Welcome to Lecture 14a, Basis Algorithms for the Kernel of a Matrix. We've been talking about subspaces and bases for those subspaces. A subspace is a non-empty subset which is closed under addition and also closed under scalar multiplication. Subspaces generalize linear objects that we can see, like lines and planes, to higher dimension. Subspaces also arise as sets, which we have been studying, like solution sets to homogeneous linear systems, eigenspaces, kernels, images, and spans. A basis is an efficient way to describe a subspace. Usually a subspace has infinitely many elements. A basis can encode all information about the subspace using a finite list of vectors. Another reason why bases are useful is that bases give us a notion for dimension. A line has dimension 1. Any basis describing a line has only one vector. A plane has dimension 2. Any basis describing a plane has two vectors. In higher dimension, the dimension of a subspace is again the number of vectors in any basis of that subspace. Here are three special sets in a subspace. We have the linearly independent sets, the spanning sets, and then a subset in a subspace, which is both linearly independent and a spanning set is called a basis. We have talked about how we can go from one of these special sets to another. A spanning set is a set which is big enough to span the subspace, but it could be too big. The number of vectors may be more than the dimension of the subspace. We have an algorithmic way to get from a spanning set to a basis. We concatenate the vectors in the spanning set, row reduce to a row echelon form, keep the original vectors corresponding to the columns with a leading one. Dually, we can start from a linearly independent subset of a subspace and get a basis. Remember that a linearly independent set is a set which is small enough that nothing can be written as a linear combination in more than one way. We can always throw in more vectors to get a basis. Unfortunately, there isn't a general algorithm that always works, although there are algorithms in some situations. In this picture, I have examples of sets which are linearly independent. The empty set is linearly independent, and sets containing just one element is always linearly independent. And I also have linearly independent sets which are of size 2. I also have here a few sets which are spanning sets for R2. Note that outside of these, there are subsets of R2 which are neither linearly independent nor spanning sets. For example, this set is neither linearly independent nor a spanning set. We have seen that every basis for a subspace V contains exactly dimension V many vectors. This is the definition for the dimension of a subspace. Every spanning set and every linearly independent set in V have sizes that are bounded by the dimension of the subspace. I have summarized these bounds. Spanning sets of V, which are not bases of V, have strictly more vectors than the dimension. If a spanning set has exactly dimension many vectors, then that spanning set is a basis. If I have a linearly independent subset of V, which is not a basis, then I know the number of vectors must be strictly smaller than the dimension of V. If I have a linearly independent subset of V, which has the same number as the dimension of V, then I know that linearly independent subset must be in here, so it must be a basis. Note that if a subset of a subspace is neither linearly independent nor a spanning set of V, there is no restriction. It can have any number of vectors. Last time we talked about this 2 out of 3 rule, where if you want to show that a subset of a subspace is a basis, sometimes instead of checking these two conditions, if you know the number of vectors and it's equal to the dimension of the subspace, then you only need to check one of these. Suppose W is a subspace, and we know that the dimension of the subspace is 4. This means that any basis for the subspace has 4 vectors. Here I have a set of concrete vectors, and I know that this set is a subset of W, and I want to check whether this set T is a basis for W, and I will use this 2 out of 3 rule. First, I want to make sure that the number of vectors in T is in fact the dimension of W, and that is true because there are 4 vectors in T. Next, I just need to check one of these 2 conditions, and I will check that T is a linearly independent set. To be a linearly independent set means that the only possible linear combination of the vectors that is equal to the 0 vector must be the linear combination where all coefficients are 0. In other words, this must have one unique solution, the trivial solution, where x, y, z, w are all equal to 0. I can rewrite this linear combination as a matrix multiplication, where I have a concatenation of the vectors times a vector of the variables. From here, I turn this into an augmented matrix, and then I perform elementary row operations until I have a row echelon form. I see that my row echelon form has a leading one in every column to the left of the vertical line. This means the system has one unique solution. So we have shown that T is linearly independent since the dimension of W is equal to the number of vectors in T, 4, and we have just done the computation to show that T is linearly independent. We have 2 out of the 3 conditions that we need to show that T is a basis. So T is a basis for W. In this lecture, we will focus on computing a basis for the kernel of a matrix. In this example, I have a matrix A, and I want to compute the basis for the kernel of A by first finding the general solution to the matrix equation here. A general solution is a description of all solutions using parameters. So this is something that we are already familiar with. First, I write down an augmented matrix and then row reduce. I will multiply the first row by 1/2 to turn this entry into 1. Next, I'll add the first row to the second row. I have arrived at a row echelon form with these leading ones. I look for the columns with no leading one and parameterize those 2. The second variable is x and the fourth variable is z. I set x to t and z to s. I do back substitution. First, I substitute z equals s to the lower equation. This gives me y in terms of s. Next, I can substitute all of these into the upper equation. I will now simplify and move everything that it's not w to the other side. I now have all of my variables in terms of the parameters t and s. So the general solution is t minus 10s from w, t from this x minus 4s from y, and s from z for t and s in R. We can use this general solution to write down a basis for the kernel of A. We just showed that every element in the kernel of A is of this form. Now I will separate the t and s. This is just usual vector addition. Next, I will write this so that I have a linear combination of concrete vectors with t and s as coefficients. This first vector becomes t times the vector 1, 1, 0, 0. The second vector becomes s times the vector -10, 0, -4, and 1. What I mean by concrete vectors are vectors with actual numbers, as opposed to here where they are returned in terms of variables. This means that every element in the kernel of A is a linear combination of these 2 vectors. By definition of spanning set, this set is a spanning set for the kernel of A. This set might be a basis, or they might be too big to be a basis. To be a basis of the kernel of a set needs to be both a spanning set for the kernel of A, which we just said it is earlier, and it also needs to be linearly independent. So we will check the second part. To check that the set is linearly independent, we turn the vectors into column vectors of a matrix and put the 0 entries to the right of the vertical line and perform elementary row operations. I see that These three rows have the same entries, so I know that I can turn two of them into a row of zeros. I've arrived at a row echelon form. I see that every column to the left of the vertical line has a leading one. This means the vectors are linearly independent. This means that our set is a basis for the kernel of A. This is the short answer for part B of the exercise, so we could have gone directly from part A to part B. In fact, this method works in general. So in the next slide, we will talk about an algorithm where we can quickly find a basis for the kernel of a matrix. The fact that there are two vectors in a basis for the kernel of A means that the kernel of A has dimension 2, the same dimension as a plane in 3 dimension. So you can think of this space, the kernel of A, as like a plane in 4 dimension. We can do what we just did for any matrix and skip some of the computation. This algorithm allows us to always find one basis for the kernel of a matrix. We put the matrix in REF form and we write a general solution to A times mystery vector equals D0 vector, and we introduce parameters for all of the columns of the REF matrix without a leading one. So the first two steps are the things that we have been doing since the beginning of the semester. We then rewrite the general solution as a linear combination whose coefficients are the parameters. Then we take the vectors in the linear combination, and following this algorithm, we are guaranteed to form a basis for the kernel of A. Warning that this is not the only basis for the kernel of A, but this is one that is easy to find. I want to now apply algorithm 1 to find a basis for the kernel of this matrix. If you are watching the video right now, it would be more helpful for your learning if you pause the video now and try on your own. Use algorithm 1 and follow exercise 2 before you watch me do this exercise. The first step of the algorithm is to row reduce. I will turn this entry into 0. I see that this row is a multiple of the second row, so I can turn this into a row of zeros. And now I've arrived at a row echelon form. I see that the second and fourth column do not have leading ones. Step 2 of the algorithm is to use this row echelon form to find a general solution. We are not given the variables, but we see that we need 4 variables because there are 4 columns in the matrix A. I will choose this one, x1 through x4. I let the second variable be a parameter and also the fourth variable be a different parameter. And then I do back substitution. I substitute x4 equals s into the lower equation. I substitute the values for x2, x4, and x3 into the upper equation to write x1 as a formula. Now I have all the variables x1 through x4 in terms of the parameters t and s, so I can write the general solution. The first entry is x1 in terms of t and s. The second entry should be t. The third entry should be negative 3s, and the fourth entry should be s. The third step of the algorithm is to write the general solution as a linear combination where the parameters s and t are the coefficients. I will do the same thing as I did in the previous exercise. I will write this as a sum of two vectors where one vector will just have t and the other vector will have only s. To write this as a linear combination with s and t as coefficients, I take out the t and the s, and this tells me that these two vectors form a basis for the kernel of A. Since we have seen a basis for the kernel of A with two vectors, we know that the dimension of the kernel of A is 2. For part B, I want to check that this set of vectors, called L, is a basis for the kernel of A. Since we already know that the dimension of the kernel of A is 2 from part A, let's try to apply the 2 out of 3 rule. First, we have to check that the two vectors of L are actually in the kernel of A. We multiply A with the first vector and check that it should be the 0 vector of height 3, and do the same thing, A times the second vector, and check that it should be the 0 vector. So L is a subset of the kernel of A, so we can keep going. Next, since we have seen that the dimension of the kernel of A is 2, which is the same number of vectors as in L, we just need to check that L is a spanning set for the kernel of A, or L is linearly independent. I will check that L is linearly independent. I take the concatenation of the two vectors in L and row reduce. First, I will swap the first row and the fourth row. And then I will turn all of the entries below this entry to 0. Next, I see that this entry can be turned into a leading one. So I will turn all of the entries below to 0. I got an REF matrix with a leading one in each column left of the vertical line. This shows that L is linearly independent. Combined with the fact that L is a subset of the kernel of A and that L has two vectors, which is the same number as the dimension of the kernel of A, L being linearly independent shows that L is a basis for the kernel of A. Sometimes we're only interested in finding the dimension of the kernel of a matrix without needing to come up with a particular basis. So by definition, the dimension of the subspace, the kernel of A, is the number of vectors in any basis. Algorithm 1 shows that this is the same as the number of parameters in a general solution. But the number of parameters in a general solution is just the number of columns in a row echelon form without a leading one. But the number of such columns is the same as counting the number of columns of A total, which is the same as the width of A, minus the columns with a leading one, which is the same as the rank of A. So to count the dimension of the kernel of a matrix, we just have to compute the rank of the matrix, and the dimension is the width of the matrix minus the rank of the matrix. For example, if I have a matrix that is 6 by 7, that means the number of columns of the matrix is 7, and I know the rank of the matrix is 2, then the dimension of the kernel of the matrix is just 7 minus 2. We will now give a summary on methods and formulas we have done so far. We have 5 standard types of subsets, which we know are always subspaces. The first two are the image of a matrix and span of column vectors. We have seen that these are the same thing. The column vectors here can be turned into a matrix. In the last lecture, we have seen a general method for finding a basis for these types of subspaces. We do row reduce and look for the columns with a leading one, and we take the original columns from the matrix A corresponding to those columns with leading one and use those as our basis vectors. We also know how to compute the dimension in general. The dimension is just the rank of the matrix. We have also seen that these 3 types of subspaces are really the same thing. All of them can be thought of as being the kernel of a matrix. In this lecture, we learn a method to find a basis for such a subspace. We can also compute just the dimension, which would be the width of the matrix minus the rank of the matrix. In each case, the dimension is easy if we know a certain rank. So we don't necessarily need to find a basis to be able to compute the dimension of the subspace. Unfortunately, for a general subspace you might encounter in the wild, which is not one of these 5 types, we normally don't know an easy algorithm for finding a basis. Next, we will review eigenspace and use the new algorithm we learned today to find a basis and the dimension of an eigenspace. Recall that if lambda is a number, the lambda eigenspace of a matrix M is the set of vectors where M times that vector is equal to lambda times that vector. In order for this product to be defined, V should be of height that is the same as the width of the matrix M. So the 2 eigenspace of our matrix M is the set of vectors in R3 where M times that vector is equal to 2 times the same vector. Let me call this set W. Remember that I can move the right-hand side to the left and get an equation that looks like this, where I have the matrix M minus 2 times the 3 by 3 identity matrix times the mystery vector equals the 0 vector. So I can rewrite my set W this way, where this matrix M minus 2 times the identity will go here. So W is really the same as the kernel of this matrix. So we have reduced the problem to finding a basis for the kernel of a matrix. We just learned an algorithm to do this, algorithm 1. We will apply that. Algorithm 1 for finding a basis for the kernel of a matrix says that we just need to solve for this matrix times mystery vector equals the 0 vector. Write the solutions as linear combinations of a set of vectors, and the set of vectors will be a basis for W. I see that all of the entries in the first column is 0, so I go to the next column. I see that I can turn this into a leading one by multiplying by 1/2. I turn the entries below this leading one to 0, and I get this matrix, which is a row echelon form matrix. I check that it has this one leading one. I see that the first column and the third column do not have leading ones, so I set the first variable and the third variable to parameters. To write y in terms of t and r, I do back substitution. I write my equation from the REF matrix and then substitute z with this z equals r. Now I'm ready to write the general solution in terms of t and r. I rewrite this so that I can have a linear combination whose coefficients are r and t. The algorithm says I can take these two vectors and that they will form a basis for W. Now that we have a basis for W, we can easily answer part B of the question. The dimension of W is 2 because we have two vectors in a basis. As a side note, if we had arrived in this REF matrix here and we saw that there had been k number of columns without a leading one instead of 2 columns without a leading one, then the dimension of W would have been k. Let's do a sanity check. We will check that at least this set that we found is a subset of the 2 eigenspace of our matrix M. Check that M times one of the vectors is equal to 2 times that vector, and also M times the other vector is equal to 2 times that vector. The first entry of this product is the dot product of this first row and the column, which is 2. The second entry is the dot product of the second row and the vector 1, 0, 0, which will give me 0, and the same with the third entry. So this vector is in the 2 eigenspace of M. We also compute the product of M times the other vector. I again get a vector which is twice this original vector. This part does not prove that our set is a basis for W, but at least we check that our set is a subset of W. This is the end of lecture 14A. We did a lot of row reduce in this lecture. In the next lecture, we will talk about ways to compute dimension of a subspace without having to do any row reduce. Thank you for listening.